Hello everyone, welcome to this explainer. We're jumping right into something absolutely fascinating today, the brilliant hidden mechanics behind how all our devices actually communicate across the globe. We use the internet literally every single day, right? Checking emails, streaming movies, firing off a quick text, but we rarely, if ever, stop to think about the invisible magic happening right behind our screens. Today, we're taking the lid completely off that system. We're going to uncover the hidden rules, the incredible illusions, and the ultimate master blueprint that makes global communication possible. So let's get into it.
All right, let's start right at the foundation. What is the fundamental purpose of any computer network? It boils down to one simple concept: sharing data. Basically, a computer network is just a collection of various computing devices. And the whole reason we connect them, whether they're totally identical, homogeneous machines or completely different, heterogeneous devices, is just so they can share something. Honestly, without the need to share data, a network has zero reason to exist. It is the beating heart of all network architecture.
Here is our roadmap for today's explainer. First, senders and receivers. Second, speaking the same language. Third, the grand illusion. Fourth, mandatory versus optional functions. And finally, the master blueprint.
Section 1, Senders and Receivers. So whenever we talk about a computer network, we're always dealing with at least one sender and one receiver. The sender is just the user or machine that's actually generating and trying to transmit a message. Let's just call it message M. The receiver, on the other hand, is the destination. It's the machine meant to actually get that data. But how does it get there? Well, obviously, it needs some kind of connection. Now, that connection can be a physical wire or it could be a wireless signal. But regardless of the medium, those packets of data absolutely must have a clear pathway to move from point A to point B.
Now, there's a really crucial distinction we need to make here. Imagine you're typing away on your laptop. You hit a key on your keyboard and a letter pops up on your monitor. The sender is the keyboard, the receiver is the monitor. But is that a computer network? Well, no. Actually, that's what we call inter-process communication. It's all happening inside one single machine, managed completely by your operating system's kernel. A true computer network only really comes into play when the client and the server are physically separated. We're talking about totally different machines, like say a client sitting in India opening Facebook, which happens to be hosted on a server in the USA. And keep in mind, the actual physical distance doesn't matter one bit here. That separation could be literally 1 meter across a desk or 10,000 kilometers across an ocean.
Which brings us to Section 2, speaking the same language.
Okay, imagine our sender uses that connection we just talked about to successfully pass message M to the receiver. The receiver physically gets it. Success, right? Well, maybe not. We have to ask a pretty critical question here. What actually happens if the receiver gets the data but completely fails to understand it? Because, let's face it, just because data arrives safely at its destination doesn't necessarily mean it's useful.
Think about making a phone call. The physical connection is absolutely perfect, but let's say you only speak Punjabi, and the person on the other end only speaks Telugu. What happens? The Telugu speaker can definitely hear you. They recognize that a message is coming across the line, but they can't understand a single word you're saying. This perfectly illustrates why a raw connection completely fails without shared rules. We've got a connection, for sure, but absolutely zero comprehension.
So, the huge takeaway here is that proper communication requires a whole lot more than just a wire. It requires a connection that is paired with a protocol. And a protocol is just a specific set of instructions running on both the sender's machine and the receiver's machine. The sender follows these exact instructions when packaging up the data, and the receiver uses those exact same instructions to unpack it. It's only when a connection is combined with a proper protocol that the receiver can finally understand the message.
Moving right along to Section 3, the grand illusion.
Think about the last time you opened a movie file saved locally on your computer's hard drive using something like VLC. You click play, and it takes, what, hardly a few seconds to start up? Now, think about opening Facebook or just doing a quick Google search. Your machine is suddenly sending a request to a server that might be sitting halfway across the globe in the USA, and yet it takes the exact same few seconds. We almost never stop to think about the fact that we're pulling data from thousands of miles away because it feels so incredibly instantaneous.
And that right there brings us to the ultimate functionality of a computer network. It is, quite literally, an abstraction, a carefully, beautifully crafted illusion. The network tricks two physically separated processes into feeling like they exist inside the exact same machine. When you log into an app, the network provides an environment so incredibly smooth and fast that your laptop and the distant server don't feel like two different machines at all. You just feel like the data is already sitting right there on your desk.
Let's break down how it does that in Section 4, Mandatory versus Optional Functions. To actually pull off this illusion in a two-way communication stream, the system relies on a whole mix of functionalities. First up, we have mandatory functions. We absolutely cannot neglect these. Take error control, for instance. The internet is an open system, right? So what if noise, or even a hacker, alters message M into message M1 while it's in transit? Error control ensures the receiver can actually detect that mistake, correct it, or at the very least ask for the data to be resent. Then we've got flow control. A sender can't just dump an infinite amount of data and completely overwhelm the receiver's memory buffer. We need constraints to prevent total network congestion. And multiflexing ensures that if you're running multiple web browsers and getting emails all at the exact same time, the incoming data actually goes to the right process on your machine. Now, on the flip side, we have optional functions. These are only used when absolutely necessary because they increase system complexity and take more processing time. Think about cryptography or encryption. If you're doing banking via an HTTPS site, you absolutely need encryption so intruders can't steal your money. But for a simple HTTP web page, totally not required. Another really great example is checkpoints. Say you're downloading a massive 500 megabyte file and it fails right at 301 megabytes. A checkpoint ensures you resume from 300, not 0. But you obviously wouldn't add checkpoint functionality to a tiny bite-sized WhatsApp text message. That would just make the whole system needlessly complex. So when you start combining all these mandatory and optional tasks, you end up with more than 70 different functionalities interacting all at once. Just try to imagine the sheer chaos if every single computer manufacturer just threw these 70-plus functions together however they felt like it. It would be a disaster. Nothing would ever communicate. That's exactly why we need strict, standardized rules.
Which leads us perfectly to our final part, Section 5, the Master Blueprint.
Enter the Open Systems Interconnect, or the OSI model. This acts as the universal standard blueprint for the entire networking world. Instead of dealing with a messy, tangled pile of 70-plus functionalities, the OSI model cleanly and beautifully divides them all into 7 distinct organized layers: physical, data link, network, transport, session, presentation, and application. This is the standardized path. Whenever you send a message from your laptop, it actually passes down through all 7 of these layers. And then, when a message enters the receiver's machine, it travels right back up these protocols before finally reaching the user. It is literally the absolute heart of all network communication.
As we wrap up this explainer, just look at this towering 7-layer structure and ask yourself what exactly is happening inside each of these layers the next time you tap send. How does an error get caught in real time? Where exactly does the encryption happen? You know, the deeper we look into this OSI model, the more fascinating this whole illusion becomes. Thank you so much for hanging out and exploring this with me today, and definitely keep questioning the magic happening right behind your screens.